Today we are going to learn how to find the modular multiplicative inverse through an example. So in this example, we are interested in finding the multiplicative inverse of 8 modulo 11. That means we are trying to find an integer b such that 8 times of b is congruent to 1 modulo 11. With respect to the 8 and 11, we know that the GCD of 8 and 11 is going to be equal to 1. So we can say here that the multiplicative inverse of this problem exists if the GCD of these two integers is not equal to 1. So we cannot find the multiplicative inverse in that case. To find the multiplicative inverse b, I will construct this table with 7 columns, which are q, r1, r2, r, t1, t2 and t, where q is my quotient, r1 and r2 are the integers given in my problem, r is the remainder, t1 and t2 are the temporary variables, and t I can compute based on this formula that t is going to be equal to t1 minus q times of t2. At the first step, to choose the value of r1, I will look at the larger integer given in my problem, and the larger integer from 8 and 11 is 11, so my r1 value is going to be 11. The value of r2 is going to be another integer, which is 8 here. The value of t1 and t2 at my initial step is 0 and 1. And for the corresponding value of 11 and 8, if I apply my division rule, I can write 11 as 1 times of 8 plus of 3. So my quotient here is 1 and my remainder here is 3. So the value of q at the first step is 1 and the value of r is going to be equal to 3. To obtain the value of t, I can use this formula where the value of t1 is 0, the value of t2 is 1, the value of q is 1. So based on this formula, the value of t is minus of 1. Then in the next step, similar to the extended Euclidean algorithm, I will do the shifting and my r2 will become r1, which is 8 here, and my remainder r will become r2, which is 3 here. The t2 will give the value of t1, which is 1 here, and the t will give the value of t2, which is minus 1 here. And for the new value of r1 and r2, which is 8 and 3, I can apply my division rule. Then 8 can be written as 2 times of 3 plus of 2. So the quotient is 2 and the remainder is 2 here. So I can put the value of q as 2 and the value of remainder r is also 2. Okay. And again I can use this formula to compute the value of t, where t1 is 1, t2 is minus 1 and q is 2. So the value of t is 3. In the next step, again I will do the shifting of columns. So the new value of r1 is 3. The new value of r2 is 2. The new value of t1 is a minus of 1. And new value of t2 is 3 here. Okay. And corresponding to this new value of r1 and r2, so I can write 3 as 1 times of 2 plus of 1. So my quotient and remainder, they both are 1 here. So the value of q is 1 here. The value of r is also 1 here. And again I can use this formula to compute the value of t, where t1 is minus 1, t2 is 3 and q is 1. So based on this formula, the value of t is minus of 4. Again I will do the shifting and my new value of r1 is 2. The new value of r2 is 1. The new value of t1 is 3. The new value of t2 is minus of 4. And corresponding to the value of r1 and r2, which is 2 and 1 here, I can apply my division rule. So 2 can be written as 2 times of 1 plus of 0. So in that case, my quotient is 2 and the remainder is 0. So this is 2 and this is 0 here. And the value of t, by using this formula, it's going to be equal to 11 here. In the next step, again I will do the shifting of column. So my r1 will become 1, r2 will be equal to 0. The new value of t1 is minus of 4. The new value of t2 is going to be equal to 11. And for this value of R1 and R2, which is 1 and 0, we know that 1 cannot be divided by 0. So we cannot find the quotient, we cannot find the remainder, and we cannot find the value of t here. Okay, and whenever you see that your R2 will become 0, so you stop there. Okay, and then the GCD between R1 and R2 is going to be equal to 1. So the GCD of R1 comma R2 is going to be equal to the GCD of 11 and 8 in this case is going to be equal to 1. Once you have the GCD between those integers which appears in your problem, and that comes out to be equal to 1, that means the multiplicative inverse exists. Okay, and the value of t1 is going to be the multiplicative inverse of this problem. When minus of 4 is the multiplicative inverse of 8 modulo 11, then we can say any integer b of the form minus of 4 plus 11 times of k, where k is your integer, is going to be the multiplicative inverse of inverse of 8 mod 11. Okay, so just by putting the value of k equal to 1, so for k equal to 1, b is going to be equal to minus of 4 plus of 11, which is going to be equal to 7. So 7 is going to be the positive multiplicative inverse of this problem. So if you are interested in finding the positive multiplicative inverse of a problem, but your algorithm is telling you that or you have a negative multiplicative inverse, then you can add this modulo m times of any integer to your solution, and that way you can convert a negative multiplicative inverse to a positive multiplicative inverse.